Okay, so let's talk about this problem here. Yeah, so you're right. What we want to do here for this first one is um, observe that since this is increasing, we can give it a name. Let's just call this left side of the equation z. Let's say call it a new variable, and then I claim that there is a one-to-one correspondence between values of y and values of z. And let me draw a picture that describes that. Let's see here. So I'm going to say, so we have e to the y plus y cubed equals sine x, and this I'm going to call z. So the relationship between z and y is increasing. I mean, the derivative, dz dy is always positive. And it's not just non-negative, it's positive. So this is some increasing, curve like that. So for any given value of z, there is a corresponding value of y and vice versa. Does that make sense? Okay. So really, if I can look at this, if I can view z as a function of x, well, for any given z, there's a corresponding y, so that means that y is a function of x. Now, how to actually do that, I haven't got the slightest, right? How to actually solve for y, no, I don't think that's even really doable. Yeah, but clearly z can be thought of as a function of x, and therefore so can y by this argument. Does that make sense? And this is a tough problem.
So z equals sine x is how we can start to the graph.
Yeah, I mean, let me rewrite this a little bit. Let me say that let's say that z is equal to, let's say h of y, and I claim that because the function's increasing, I claim that this h function is invertible, and so therefore y is h inverse of z, and this is actually okay because it's an invertible function. Right? And then furthermore, now clearly z is a function of x. That's an easy function. Z is sine of x. That's certainly okay. So altogether then, y is h inverse of z, but z is f of x, and this then is a composition of two perfectly good functions. So therefore y is a function of x. Yeah. Okay. Let's talk. Do you want to talk about the second part also?
Yeah, it wasn't sure.
So the path of the yeah. I have to look at the details here. Let's see. So 265. Let's see. Do we have? Oh, we have a result here. Okay. Yeah. Good. Somewhere.
Yeah.
Okay. Yeah. Here we go. So here's position as a function of theta. Yeah, so the same kind of thing happens here. So notice that x is an increasing function of t, theta. Excuse me. So I can solve for I can solve for theta in terms of x. Let me write this down. Similar kind of thing. So we have that position is, well, I have, I don't want to use the variable name. Let me call this f of theta, g of theta to represent x and y. Right? And I claim that f prime is always positive. Right? Because if I can compute f prime, well, see here, f was 16 theta plus 8 cosine theta. That means that f prime is 16 minus 8 sine theta, and I claim that this is clearly always positive, right? Because 16, this is no bigger than 8 here, so so if f prime is always positive, that means that if I were to draw x as a function of theta, it's always doing something kind of like that maybe. And so in particular, again, because it's always increasing, this is an invertible function. And so I can talk about f inverse. This is x equals f of theta, and I can talk about f inverse, and it's okay. So what is y? Well, y is g of theta. Theta is f inverse of x, and so therefore y is a function of x, and that function is g compose f inverse.
So
Same basic idea as the first part. It's just different details. Yeah, and we're kind of using that same hint that critically the point is that this function here is always increasing, and therefore I can invert it. Yeah, this is a hard problem. Let the record show. Definitely a hard problem. Let's see. This was number 2 here. Yeah. Okay. Hang on a second.